So, good morning everyone. I'm the last one this morning. So today we talk about emergency landing using deep storm for airborne wind energy system with sky. So the only missing person here is Gina Labona. She is my co-advisor in airspeed one. So the talk has four sections. First I will introduce, then I show the modeling part, I formulate the problems, and then I show simulation results. So, as we already know, launching and landing phases are some of the most promising phases in airborne wind energy system. So the figure here you can see the fundamental of airborne wind energy system. We have the kite rolling in and rolling out to generate energy. And on this figure, you should see a figure from the transition from taking off to pumping cycle. We missed one figure from the transition from pumping cycle to landing phase. That's why they say it's a promising research topic. For fixed wing kite, there are some models that you already know, the M6 power and the kite vehicles. And now a model in the labs from UPOC. So the proposed idea are the following. First, the kite will use deep storm to land. So near the ground, the kite has to escape deep storm. And there are three options to do that. The first two options are from the FAA, that either the kite pitching down or to increase the force, to increase the airspeed, or we employ the VTOL mechanism. And finally, the kite could fly to land or perch to land. So I will demonstrate the top by the bold text. First I will demonstrate deep storm, increased thrust, and perch on the net to land. All flying aircraft are subjected to four forces that we already know. And our main focus is the lift force. So the lift force has the most common equation as a function of the air density, airspeed, landform area, and the lift coefficient. Where the lift coefficient are usually modeled as a linear function of the angle of effect. You can see in this figure, with the most small region of angle of effect, the lift coefficient is a linear function. However, when we go further right, the lift coefficient have a drop here due to what they say a vertical angle of effect. So aerodynamically it's because of the boundary layer separation effect. But if we go longer in that region, we go to deep storm. So deep storm is defined as a very large angle of effect that are developed after the storming angle has been achieved. And in 1984, NASA executed main control deep storm maneuver. And they say that the stable angle of effect are in 30 to 72 degrees. In real life application, there was only one company that utilized deep storm landing in their UAV. It's the Raven 3 UAV. You can find in the fact sheet of the company and YouTube videos. For perching is another force-storm maneuver that is a bio-inspired maneuver from the birds, which utilize the high drag force at a large angle of effect to braking. So you see the images of the perching maneuver here from Stanford. First, the bird pitch up, open the wings to have more drag, and then perch on the branch here. Okay. You have to remember this image. We will see this image later. So the difference between perching and deep storm is, for perching, you have higher angle of effect up to 90 degrees and lower final airspeed, very low, could be 0. And for perching aircraft, there are two main research interests, either normal aircraft or morphing aircraft. Morphing aircraft are aircraft with the wings could change the dihedral angle, the wing sweep angle on the tail side to make them look like birds. I'm not doing this, I'm doing just normal aircraft. Now modeling. For modeling, I use the textbook model from small unmanned aircraft theory and practice model. I just want to mention that I put the net right above the initial frame origin here. Okay. The main focus here is the aerodynamic coefficients for the postbone regime. So there are two popular reports from NASA. One is the postbone wind tunnel data for NACAP for XX, and the other one is the aerodynamic characteristic for 7 symmetrical airfoil. So I opened one of these reports, and we see that for the lift force, the first small angle of back regime is a linear function. For the postbone region, it looks like this is a periodic function of the angle of attack. For the right force, a similar behavior. This is like a linear function, and the postbone is like a periodic. And for the pitching moment, a linear function is enough to fit. Okay, now I open the other report. For the lift force, we also see the same behavior: linear, drops, and then periodic. This is like look like a quadratic function, and then periodic. For the pitching moment, it's like a linear function. So we use a blending function to match to regime. So this sigmoid function here is like a step function from 0 to 1, but the place where the step occurs is at alpha 0. Okay. So for the restore regime, we use the textbook formula in the fundamental of aerodynamics. And for the postbone region, we see that the flat plane theory is enough to fit the postbone regime. Okay. Now I formulate the deep storm with perch landing. This will be the trajectory tracking problem, which composed of two tasks. The first one is to generate an offline overlook constraint optimal control problem. And the second task is the tracking task, to track this trajectory with bounded gears, to check the effectiveness of the nonlinear model with this control. So how we formulate the trajectory generation? We minimize the cost function, which is composed of the thrust and the input deviation. We see that both deep storm and perch can be executed without thrust. And for the input deviation, we don't want any abrupt behavior. Subject to the aircraft dynamics, input constraint, state constraint, boundary initial state constraint and input constraint. These conditions are based on the steady level flight of the kite at the beginning. And the final state constraint. Notice that here we have two different state constraints for the state, and I will explain them later. Here. So you see the origin is here. This is 0x, and z is pointing down. We put the net right below the 0. Okay. So I will not try to explain this figure now, but I will explain after the MBC formulation. But I just want to focus that in the generation task, I make a trick that I set the theta to be larger than 0. This is the trick. Okay. And also for the perching, I want the angle of attack to be larger than 90 degrees. So the XG2 is the set after the net, and XG1 is the set before the net. Now this is the projection on the airspeed and X plane. So we want in the generation task, the constraint is tighter than the one in the MBC task. The MBC is the best one I will talk about. Okay. Now for model predictive control, as you already know from my colleague Manuel. So at the time instance T, the controller tries to minimize the error between the state and the reference to often the set of input, and then we only apply the first input, and then the procedure is repeated. So to track the reference trajectory, we minimize the error between the current state and the reference state value. the current input and the reference input from the previous problem. We also put the terminal cost, but notice that this work will not focus on the stability of MBC, which is an application of MBC. Subject to the aerodynamic, the input constraint, the state constraint, the initial state constraint, and the terminal state constraint. Now we see again these two figures. So the state constraint for the MBC are the two direct that we call the line of sight corridor. No matter what happens, the state has to stay inside the red corridor. Yeah. So the wind trajectory here is the reference trajectory, and the blue is the MBC trajectory. You see that at the end here, we have a dot and dash trajectory. This is the predicted final trajectory of the MBC. We don't care about the part beside the net. We only care about the real trajectory until the net. But we need an extension for the controller to track. That's why we have the extension also from here. And in the generation task, we have like a constraint tightening technique. Like we constrain the state to be smaller than what we want, so that in real life with girls, the state will stay inside the wet corridor. That's the idea. Now, simulation result. For simulation result, I use the model also from the book. And this is the aerodynamic coefficients. You see the vertical angle of attack is 24 degrees. After that, the lid is off, and then we have a curve. For the wax, the wax is increased in the postpone region. Physical parameter in case anyone wants to ask. And now I show some videos. So I will explain this. So this is the longitudinal plane, the x and the minus z, because that is pointing down, so I have to put minus z. The control input delta E is the elevator deflection here. Delta T is the force. Velocity, you have the airspeed, the longitudinal x dot, the vertical z dot. For angle, you have the angle of attack, the theta, and the flight path angle. The flight path angle is the tangent of the flight path. For lift and drag is here. Pitching moment is here. And omega is the pitch range is here. So I will play this video many times for you to see. Because you cannot focus on multiple figures at the same time. So the plane is now in the deep storm mode.
Is that an elevator, what we see here? Is that the elevator?
Yes, this is the elevator. The ego is Notice that in the first stable deep storm, nothing changed. It's another stable stream state.
Attention please, attention please. This is the test of the fire and voice alarm system. There is no need to take any action. Attention please, attention please. Fire has been reported in the building. Please leave the building immediately by the nearest exit. Do not use the lifts.
Now we analyze this figure. How many people understand the figure here? Nobody. So at the beginning, the plane was in steady level flight. Okay, we forced the airplane to minimize the thrust, so that it minimized the thrust.
Attention please, attention please. The test of the fire and voice alarm system has now been completed.
The elevator is pushed up like this to pitch up the airplane. For pitch up, you have to see the theta angle. Theta is increased here. And then the plane falls into the stone state. The vertical angle of attack is this line. The plane falls into the stone state here. The lift is increased because the elevator is decreased. Okay? So after the plane stalled, the lift lost. We lost the lift here. Okay? And then in deep stall, the lift is regained. Drag increase. Pitching moment, pitch up, pitch down, and then stall. Deep stall. Same with pitch rate. Okay, so in deep stall, I will not analyze because it's just a stable state. At the end, for purging, let's see. To purge, the airplane increase the thrust here to escape deep stall. Here. Now, what happens next? Lift is feed this. You have more lift after you escape the stall. And then for purging, purging is delta E. You increase delta E. Increase angle of attack here, increase drag here, and you lost the lift. That's what happened. Okay. No, I have more. I have more.
But we are also at the lunch break.
Yeah. Quick. Now I do multiple initial position. So instead of just one point, we have to see the bundle. They will not behave the same. The same optimization problem, different initial state. This far left here. It will go the fastest down here. In this segment, I don't know what happened here, but they come together.
Yeah.
Now for the NDC, only last video. Explanation. So you have the gust here, the NDC computing time is here, the gust here, and the tracking result is here. Yeah, I put this bounded disturbance between 0.2 and minus 0.2. Unknown disturbance. Anyone has questions? I finished.
This is a nice example for bionic-inspired maneuvers. What was the original intention to have this? I think maybe I missed this. I mean, why do you do this deep stall landing maneuver to achieve what? To come as quickly as possible to the ground?
In a stable mode.
In a stable mode.
Yes.
To land or?
It will crash. But if you have the punch here, it will land.
Okay. Any other questions?
Yeah, thank you. I think this is really cool. So I was curious, have you considered how the tether would affect things during this maneuver? Are you assuming that you have a lot of tether slack, or is this more of an emergency landing procedure after the tether is ruptured, or yeah?
I assume that the tether doesn't exist.
Do you think including the tether would significantly change the results of the outcome?
No. You just lose the tether, and then you land yourself.
All right, cool, thanks.
We have very good models to simulate that. Any other question?
Very interesting. Did you consider lateral stability?
Not yet, only longitudinal. But there are work from perching with lateral perching. There are work from it.
Any other question? See any then? Thank you again.
Thank you.